Hey, there we go. So good morning, everybody. Still getting used to people without masks in large areas. So learned control. So to jokingly start, so making fiber is really easy. Manufacturing fiber is hard. Making coffee, I made some this morning, easy. Manufacturing coffee at scale is hard. Making an engine, maybe it takes a little bit more to make an engine, and it takes a lot more to manufacture an engine. So we are moving towards an era in process control where we can benefit from machine learning, deep reinforcement learning techniques to make manufacturing that's hard in terms of getting high rate, good quality, controlled processes. So we're focusing on feedback control, and I contrast that briefly with statistical process control. So feedback control is this idea of I have a metric that I'm trying to control my product, whether it be the diameter of a fiber or the temperature of coffee being roasted. And I want to control that with some level of precision. Right? And feedback control takes care typically of the deterministic sources of variation in your system. Compared to statistical process control, once you've implemented your feedback control, it's dealing with the random variations. I'm focusing here on the feedback control. So what is feedback control? On the graph here, we're seeing a draw tower. Actually, it's a mini draw tower. This is a smaller version of the sort that makes an optical fiber, the 125 micron optical fiber that's the backbone of wireless communication. Right? It's the trunk lines for getting our data all over the world. This is a 3-story version. The production scales are 5, if not taller. And in this process, there are many different things that we're controlling. We're controlling the speeds, the temperatures, the diameter, not the roast color of the fiber, roast color if we're controlling the production of coffee, for example. And 90%, 95% of the world, and you walk into the manufacturing floor and say, well, how are you controlling your processes? They're going to be using typically a PID controller, proportional integral derivative controller, right? So it's a workhorse engine, it works very well. And basically that means this controller takes the error signal, the difference between what you want and what you're getting, and decides to apply control effort that's either proportional to your error, proportional to the derivative of your error, or proportional to the integral of your error. Now, that's great, right? But there's some unique challenges associated with processes that have a lot of drift, either in the materials, or that are complex physically. If there's a lot of complex thermal, fluid, electrodynamics going on, operating sort of a controller around a set point benefits if you have a good model of your system. Right? Some of these systems are really hard to model. Complex, even with fiber draw, is a complex heat transfer, mass transfer problem that you could write down the couple differential equations and come up with a great model. But it's hard to do from first principles. So we're taking this idea of, let's look at the areas where proportional integral derivative classical control breaks down, where it's really good at nominal set points, but if we need to retune or control a process that has complex dynamics, and I could benefit from better models, how do I do that? So our approach is bringing deep reinforcement learning to the edge, or integrating, if you will, the stuff that you would do on Amazon and the stuff that you would typically do on the line. So on the line, you're using controllers to compare your error, your thing you want, the thing you get, and then you would collect data on that process, and you say, well, let's do the data analytics, so let's go do our deep reinforcement learning on Azure, Google, pick your platform of choice. But can we actually bring that to the edge? Can we bring that learning and have that offline learning happening online to improve our models and to change the way that we do real-time control? So your manufacturing process, you have material and some data in set points, you have machines that are doing something, roasting coffee, drawing a fiber, and you have products and data. We use that data. So this is the canonical graph, if you will, of a deep reinforcement learning sort of setup, but I sort of highlight 2 pieces. The blue box is I have a machine and something's happening on that machine. I'm taking some measurements, I'm doing some control. So that piece of the deep reinforcement learning engine looks like the control system. Looks like a controller adjusting some signal based on an error and telling my machine to do something. And then the rest of these pieces, these are all the machinery that we use that would typically be logging that data and sending it off to the cloud. But let's log that data and not do big data, but do big enough data that fits on the processor that you can have be running adjacent to or be the programmable logic controller that's doing the control, so that I can iteratively improve my controller with a dynamically learned model. So we have a paper out that's on this, specifically doing this on dynamic control of fiber, the 100 micron, 125 micron type fiber that, as I mentioned, is the backbone of our wireless communication. We're in the process of, with company partners, doing this for coffee roasting, which is a very different process. It's a continuous batch process, and also doing it for a food packaging process. So we think there's some really unique opportunities in moving how control is done. Now, a critical piece of this in the last 30 seconds is learn control is one thing, where I can integrate for de novo, if I'm starting a control system from scratch, I can design my system the way that I want. But how do I go attack the entrenched millions, billions of dollars of existing control systems? So we've had to develop this deployment process, where we'll take the sort of approach that you have data now, you have a conventional control system now. Let's learn some models, use those models to tell you how to retune your existing controllers, then move that process to be happening, that retuning happening instead of manually one time, continuously, working on the backbone of a PID controller, then work to the point where we have now probably the new hardware that's a slightly more robust version of a PLC to run the deep reinforcement learning piece, and then sort of put that all together. So would love to talk to folks about both your applications. Yeah, we are still doing this in the context of academic research, and these are the students that have been working on various aspects of this. Xenia is in the back. She set up the poster, and Ani will be over there at the poster this morning as well. But please come by and chat. We'd love to talk about applications, and thank you.
Thank you.